We're going to take a look at polynomials and a little bit more graphing again today. A polynomial is one or more terms added together where the exponents and the variables are positive whole numbers or possibly zero because x to the zero is 1, and so that would just be a normal number. You cannot have any fractional exponents. You cannot have any negative exponents. You cannot have variables in the bottom of a fraction. So just be aware of that for polynomials, and polynomials will come up to play later as we use that to define another function. So we're going to take a look at the intermediate value theorem. Intermediate value theorem, if you have a polynomial where you have 2 points that are at different heights, so one's above the other, we don't know which one's above the other, we just know they're not at the same heights, and your 2 input values are different, where A is to the left of B. Therefore, to be able to go from your output at A to your output at B, it has to take on all the values between these 2 different outputs. And you might be wondering, so what? Well, consider this situation. If at A you're below and at B you're above, we would have to say it somehow has to cross the x-axis or have a 0 somewhere in between A and B. Now, if we know we're down here and we know we end up over here, we don't know how we get there. We could come over and cross close to B. We could come up and cross close to A. We could come up, come back down, touch, and then go back up. But to be able to go from here up to here, we know we would have to cross the x-axis and have a 0 at least once. So that's the consequences of the intermediate value theorem, where if you have one point that's output's negative, one point that's output is positive, it has to cross in between the 2 x values. So use the intermediate value theorem for this particular problem here. Well, we want to show that we have a 0 between a half and 3/4. Well, we got to figure out what the output is when you plug in a half. So we'll plug in a half for our x's up here, and we get negative 9/8. So in other words, we have a point 1/2 negative 9/8. Well, then we got to plug in 3/4. And we get positive 41 over 128. So we have the point 3/4 comma positive 1 over or positive 3/4 41 over 148 or 28, sorry. So we plot those 2 points. So we have one point that's below at a half, we have one point that's above at 3/4. So the only way to go from here up to here with a polynomial, which is continuous, is to somehow cross in between. We don't know where we cross, so therefore we can write this. And write this down because you will have to be writing out this sentence once you get to your test. Sits at 1/2, you're below the x-axis, and at x equaling 3/4, you're above the x-axis. We can say by the intermediate value theorem that the graph must cross somewhere between 1/2 and 3/4. We're going to go ahead and try to graph this function, but we're going to try to figure out where it crosses the x-axis first, and also where it's positive, meaning above the axes, and where it's negative, meaning below the axes. So since we're looking to see where it's greater than 0 or less than 0, we're going to figure out where it is 0, because that means those will be the points that separate it from going to positive to negative. So to solve something like this, we're going to factor it, greatest common factor, then we do our AC factoring, and in this case we get 0, -4, and +1. These are what are referred to as your critical points. You put these critical points in your number line. They divide your number line into regions that are positive and regions that are negative. So let's consider this. Let's try a number over here like -5 in this region, because we want to plug it in to see if it's positive or negative. I like doing it into the factored form. Plug a negative here, squared is positive. -5 here plus 4 is negative. -5 minus 1 is negative. Negative times a negative is positive times another positive means it's positive over here. Then we could try a number in between. Doesn't make a difference what. We could try like negative 1. Negative 1 squared is positive. Negative 1 plus 4 is positive. Negative 1 minus 1 is negative. Positive times positive is positive times another negative is negative. Then we could try something in here like 1/2. 1/2 squared is positive. 1/2 plus 4 is positive. 1/2 minus 1 is negative, so it's not going to change. It's going to still be negative. And then we can try a number over here like 2. If we plug in 2, we get positive here. 2 plus 4 is positive. 2 minus 1 is positive. Everything's positive. When you multiply all positives, you get a positive answer. So we would know, off of our number line, we want to write, where is it greater than 0? Well, it's greater than 0 over here in the purple and to the right over here. So to the left of negative 4 and to the right of positive 1. Since we have two totally separate regions, we join them with an OR statement. Then we want to know, where is it negative? It's negative in this region between negative 4 and 0. And then there's another region from 0 to 1. You might be wondering, why didn't we just go negative 4 all the way to 1? Well, we need to be less than 0. And at 0, 0 causes us to actually be equal to 0, and we need only less than. So at this point, let's go ahead and sketch ourselves a graph. We'll graph our critical points of where we cross the x-axis. Now, because we know we're below negative 4, or between negative 4 and 0, we're below, we got to cross here, we got to cross here, and in between we're below, so we know we're down here. We don't know how far down it goes or anything like that. We also know between 0 and 1 we're below, so it's going to be another smile. Now, to the right of 1, we know we're above the axis, so to the right of 1, we know we got to be up here. To the left of negative 4, we know we got to be positive, so that means we're up here. So that's your basic sketch of your graph. We know where it's positive and where it's negative. Now, your turning points are kind of where it switches from going down to going up. So that would be about here. It switches here, and then it would switch here. So that would be our turning points. We also know from our work where we cross the x-axis, which are at these spots.